Hello, I'm James Rango, editor of Electronics Cooling. Thanks for attending Thermal Live. For our next presentation, John Grisdale, Chief Growth Officer at Sur-Seal, and his colleague Greg Silzeski, Technical Business Development Manager, are going to highlight how thermal interface materials work, the different types of materials available on the market, and how to choose the right one for your application, leaving you with the knowledge necessary to make educated design decisions in your next application that requires thermal interface materials. If you have any questions, please use the Q&A box below. They will try to answer as many as they can at the end of the session. Without further ado, Sur-Seal, please take it away.
Good afternoon. I'm Kate Portledge, Senior Director of Marketing at Sur-Seal. We are excited to be part of our first Thermal Live. I'd like to introduce you to John, our Chief Growth Officer, and Greg, our Technical Business Development Manager, who are going to take you through our presentation today. Thermals Made Easy.
Thank you for joining the Sur-Seal Company today. We hope that you find our presentation on thermal interface materials to be informative. But first, before we begin, I wanted to share a little bit about our company. Sur-Seal was founded over 50 years ago as a family-run business. Today, we are headquartered in Cincinnati, Ohio, and have engineering service centers in 5 additional locations. We do business with over 200 original equipment manufacturers and are known for our customer service and engineering expertise. Here at Sur-Seal, we help design, engineer, and manufacture components to solve for a variety of challenges, including protection, cushioning, stabilizing, and sealing. And of course, what we're here to talk to you about today, thermal management. We make components through a variety of methods, including die cutting, slitting, and molding. And now I'm going to turn it over to my colleague Greg, who's going to share more about the material types we work with. We will then dive into why we're here today to discuss thermals.
Thanks, John. Sur-Seal can make components from all of the standard materials such as rubber and textiles, and also have our own proprietary materials that we offer our customers. We just introduced this new line of thermal interface materials, which we would like to tell you more about by the end of the presentation. Before we can discuss how to select a thermal interface material, we need to understand why TIMs are used and the science behind how they work. For our example today, we will be using an LED. The LED is the heat source, which is on a printed circuit board assembly, or PCBA. The PCBA is then mated to a heat sink, which is presumably a larger metal housing. In this application, heat is moving from the heat source to the heat sink via conduction. However, this transfer of heat is not perfect because the PCBA typically remains hotter than the heat sink. Why is this happening? If we were to zoom in and on the mating surfaces between the PCBA and heatsink, we would see that the surfaces are not flat. The PCBA and heatsink mating surfaces are full of peaks and valleys with some metal-on-metal contact, along with a large amount of air in between. It's these air pockets that are preventing heat from transferring efficiently from the PCBA to the heatsink. Air has an extremely low thermal conductivity, meaning that it is an excellent insulator and poor conductor of heat. The result is that nearly all the heat transfer must now take place where there is a metal-on-metal contact, which may be a fraction of the overall surface area. In order to improve the heat transfer from the PCBA to the heatsink, we need to replace as much of this air as possible with a material that has a better thermal conductivity than the air. This is where thermal interface materials come in. Good thermal interface materials conform to the peaks and valleys of the mating PCBA and heatsink, replacing nearly all the air with a material that has a much higher thermal conductivity than the air. This facilitates greater heat transfer between the PCBA and the heatsink. The first item is fairly straightforward. You should know how many degrees you need to lower the temperature of your heat source. If you need to hit a specific target steady-state heat source temperature, make sure to make note of what the temperature is, as well as what the steady-state temperature of that heat source component is without any thermal interface material present in your assembly. Together, these pieces of information tell you how much improvement you need to make by adding a thermal interface material. The next most important factor to consider is what your budget can handle for a thermal interface material. We'll talk in more detail later in the presentation about the different factors that affect the price of thermal interface material, but having a general idea of what you could spend is a good idea before beginning the selection process. The last thing you want to do is get to the end of the selection process just to find out that you blew your assembly budget wide open and now need to start everything from scratch. The last item to take note before starting the thermal interface material selection process is your assembly configuration. This includes your heatsink, heat source, and other mating and fastening methods. We'll elaborate more in the next slide on the importance of understanding your assembly limitations prior to starting your search. When looking at your assembly configuration, there are three primary features that you should take note of prior to beginning the thermal interface material selection process. The first is the configuration for your heat source, which is typically a printed circuit board assembly. It's key to understand whether you're trying to move heat away from the entire board or just from a certain component of the board. This will give insights into how smooth the surface is that you're trying to make the thermal interface material. Aluminum backboards and heat sinks will be more rigid, while materials such as FR4 will be less rigid and thus more likely to bow under pressure. This is critical in determining how firm of a thermal interface material can be used. The next feature in the assembly that you should take note of is your heat sink. While most applications will have a traditional heat sink, such as one shown here, other assemblies may be less robust. Things to note from the heat sink include size, rigidness, and surface finish. A large, smooth, and rigid heat sink will provide best mating surface for thermal interface material, but often assemblies are not so fortunate. The last aspect of your assembly that you should analyze is the method by which you are fastening the heat source to the heat sink. Ideally, you have multiple bolts applying even and adequate pressure across the board, such as the assembly picture shown here. However, it is common to see uneven and poor pressure, meaning that firmer materials may be less suitable for your application. Now that you know how TIMs work and what aspects of your design you should be aware of when starting the design process, you're ready to start the selection process. Selecting the right thermal interface material for an application is as much of an art as it is a science. There are multiple factors that need to be considered when making a selection, and each factor typically affects the others. The three primary factors that need to be considered are function, performance, and last but certainly not least, price. The first factor that needs to be considered is the functionality of the thermal interface material. One must consider whether they need a TIM that provides only improved heat transfer or a TIM that also provides additional functionality. Some examples of additional functionality includes electrical insulation properties, where the TIM is acting both as a thermal conductor as well as an electrical insulator. Other examples of multifunction thermal interface materials are those that act as bonding agents or perhaps that double as a seal, in addition to their roles as a thermal conductor. By first identifying what functions are required from the thermal interface material, designers can quickly narrow down their choices. One material aspect that affects both performance and functionality is the addition of pressure-sensitive adhesive backings. Pressure-sensitive adhesive, or commonly referred to as PSA, are often required in a design to assist with assembly. If you find that a PSA is needed to help in the assembly process, be sure to choose a thermal interface material that is compliant with PSA. Not all thermal interface materials are capable of having an adhesive backing added, so identifying this functionality at the start of the design process is critical. One last thing to note about adding adhesive layers to your thermal interface material: oftentimes adding a layer of adhesive to the thermal interface material will degrade the performance of that material to a certain extent. Since you are introducing another layer of material for that heat to transfer through, you are thereby increasing the thermal resistance of the system. This is just something to keep in mind as you begin your selection process. The real-world performance of a thermal interface material is primarily dependent upon three main factors. The first critical piece is that the material chosen will need to be thick enough to fill in all the air gaps between the mating surfaces and soft enough to conform to the surface irregularities. The size of the air gaps is dependent upon multiple factors, including the surface roughness of the mating surfaces, as well as how flat and parallel the mating surfaces are. You will also need to consider how these air gaps may change over time as the assembly is built. After this, the most important factor is the thermal conductivity of the TIM material. Thermal conductivity is a property of the material and indicates how well a material transfers heat. This is a measure in watts per meter Kelvin. The higher the watts, the higher the thermal conductivity, and the better it transfers heat. There are some trade-offs to keep in mind here. For one, in some cases, a material with higher thermal conductivity may be less compressible. A higher thermal conductivity does not necessarily predetermine better thermal performance. The next factor determining real-world thermal performance is the thickness of the material. While stated earlier, then the material must be thick enough to fill in the air gaps, excessive and unnecessary thickness will hurt thermal performance of the system. It is critical to find the right thickness of material for a specific application. This is not a one-size-fits-all approach. Last but certainly not least is price. Finding a thermal interface material at a price that fits your product is crucial. And so knowing what factors typically tend to affect price is helpful in guiding your decision. Typically, the higher the thermal conductivity of the product, the higher the cost. Additionally, materials typically become more expensive as the thickness increases. Now that we've covered the different selection criteria to consider when choosing a thermal interface material, we can discuss the different types of thermal interface materials commonly used. We'll cover the pros and cons of each material type, including when it's most appropriate to use each one. Sur-Seal has its own line of thermal interface materials sold under the Sharecool brand. This line of thermal interface products is a concise offering that covers a wide array of applications. The product types include gap-filling pads, electrically insulating TIM sheets, thermal tape, and thermal phase change material. Some other product types that are not included in the Sharecool line, but which are commonly used, include thermal grease and graphite materials. We'll also cover some less common thermal interface material types which you may have come across from time to time. Our goal is to give you a comprehensive overview of the options available in the market so that you have a working knowledge of each. Thermally conductive gap-filling pads, commonly referred to simply as a gap pad, are some of the most versatile thermal interface materials available. These products come in a wide range of thicknesses, firmnesses, and levels of conductivity, making them the Swiss Army knife of thermal interface materials. Thermal gap-filling pads are typically thicker and softer than some of the other material types. This means that thermal gap pads shine in applications with larger gaps, especially with two mating surfaces rough and unparalleled. They are also ideal in low and uneven pressure applications thanks to their extremely compliant nature. Many gap-filling pads also provide electrical isolation benefits. One drawback to gap-filling pads is that higher performance grades can be on the more expensive side, with costs generally rising as the material becomes thicker. One common application for thermal gap pads is in the telecommunications equipment. In these applications, thermal gap pads are used to span the uneven and large gaps between heat-sensitive components on the electrical assembly board to the metal housing heatsink. In many applications, there is a need for not only improved heat transfer between components, but also for added electrical isolation properties. It's in these types of applications where dual-purpose products shine. These products are often referred to as thermally conductive electrical insulators, working as a highly effective thermal interface material that also provides superb electrical isolation properties, all in a thin, puncture-resistant sheet. While great for many applications, these electrically insulating sheets tend to be less thick and a bit firmer than gap-filling pad, so they may not be the exact right fit for every application. A very common application for these types of products are between power transistors and their mating component. The thin material fits nicely beneath the transistors, creating a path of improved heat transfer, but with a robust electrical isolation. Another example of a dual-purpose TIM product is thermally conductive tape. In applications that require both mechanical bonding and improved heat transfer, thermal tapes are a perfect fit. They can be used to simultaneously improve the structural and thermal performance of an assembly. Some thermal tapes even have the added electrical insulation properties. One thing to keep in mind when designing with thermal tapes is that they are often not reworkable, meaning that once they are placed into an assembly, they cannot be repositioned. A common application for thermally conductive tapes is for mounting LED strip lights. In these applications, thermal tape is not only improving the thermal performance and extending the life of the LEDs, but is also helping hold the LED strip in place in its final assembly. Thermally conductive phase change materials combine the high thermal performance of grease with the ease of use and long-term resilience of a die-cut pad. At a specified elevated temperature, the phase change material undergoes a transformation from a solid state into a gel-like state. This change of state allows the thermally conductive material to fill in all the microscopic gaps between the two mating surfaces, replacing air with an extremely thin conductive bond. The result is a high-performance heat transfer, ideal for use in applications with thin gaps and low clamping pressure. The drawback to these products is that they are primarily intended for applications with very thin air gaps and will not be suitable for uneven or unparalleled surfaces. A common application for thermally conductive phase change materials is in high-powered TPU applications. These applications typically demand high-performance heat transfer. They also commonly provide smooth and flat surfaces to mate against, but without excessive application pressures. This combination can make an ideal spot to utilize thermal phase change materials. Thermally conductive grease is perhaps the best bang for your buck product, providing great heat transfer with a low unit cost. Like the phase change material, grease does a great job of filling in all microscopic gaps between the two mating surfaces, leading to superb heat transfer. However, grease comes with its fair share of challenges. Beyond the difficulty of handling and applying the grease easily and consistently, grease can also be subject to a phenomenon such as pump out, which can degrade its performance over the long term. Similarly to thermal phase change materials, grease is a common choice for use in CPU applications. Grease's ability to deliver high performance heat transfer by eliminating air gaps make it a strong candidate in demanding applications such as this. The last of the common thermal interface materials we will discuss today is graphite. Graphite comes with some unique properties such as anisotropic, meaning that it has different thermal conductivities in different directions. The result is material that not only can move heat from a hot component to a cooler heat sink, but that also helps spread the heat out and remove localized hot spots. Ultimately, this leads to some unique and high performance heat transfer capabilities. Two things to keep in mind when designing with natural graphite is that in its bare state, the material is both electrically conductive and somewhat brittle. An example of an application that requires the unique heat transfer properties of graphite would be in handheld electronics. In these types of applications, designers need to not only improve thermal performance, but they also need to shield the user from localized hotspots. Graphite's natural heat spreading abilities allows it to tackle these challenges by not only helping to remove heat from a system, but to spread it over a larger area, leading to a more satisfying user experience. While the previous 6 thermal interface materials are some of the more common types of TIMs you may find, there are some other less common types that you should be aware of. First is the use of metals, including aluminum as a thermal interface material. Typically, aluminum and other sheet metals are used primarily as mechanical and structural components, but they can also double as a thermal interface material. This makes them useful in these scenarios, but their high cost and low compressibility make them less ideal in traditional TIM applications. Another less common thermal interface material is potting resins and epoxies. These materials often serve a greater purpose than simply thermal management. Typically, potting compounds are used to protect an electronic assembly from the elements, whether that be dust, water, or vibration, and to improve thermal performance of the assembly is an added benefit. When considering all these factors, the selection process for a thermal interface material application can seem overwhelming. Many engineers have told us that it is typical for the thermal interface material selection process to seem like guesswork. For Sharecool, we're aiming to change that by giving engineers the real-world data, clarity, and confidence needed to make educated and informed design decisions. There are well over 300 different thermal interface materials available on the market today, from a wide variety of manufacturers. Sometimes these products have only small differences, and it is often unclear why someone may need so many different options. This is why the Sharecool product line is intentionally concise yet versatile. By having a clean, concise product offering, Sharecool is able to cover 75% of all thermal interface applications, with a product line that is much slimmer and easier to understand than others available today. We'll quickly review the different grades available in the Sharecool product line. The 4 different product categories that make up the Sharecool line include thermal gap pads, the Sfr Series, thermally conductive tape, and thermal phase change material. Sharecool thermal gap pads deliver on the promise of flexibility and ease of use. They're compliant and easily compressible, making them the ideal Sharecool material option for low pressure applications. They also come in the widest range of thicknesses and thermal conductivities, allowing them to span any gap and to address any level of performance needed. Sharecool thermal gap pads are available in 3 different tiers: ultra soft, standard grades, and performance grades. Ultra soft grade is highly conformable, ideal for very low pressure and very uneven surfaces. The standard grades of Sharecool thermal gap pads are available in 1.5 and 3.0 watts per meter Kelvin. They are cost effective and a great way to remove heat from a system without adding too much cost to the assembly. The performance grades of Sharecool thermal gap pads provide the highest level of heat transfer performance, providing excellent conformability as well as a 5 to 8 watt per meter Kelvin thermal conductivity. The Sharecool Sfr Series is our family of thin, thermally conductive, electrically insulating sheets. These products provide superb electrical isolation in a very thin format, while also greatly improving heat transfer between the heat source and the heat sink. All products are puncture resistant and low tack, meaning they're ideal for repositioning. Additionally, all products are available with adhesive on one side in order to aid assembly. The Sfr series comes in 4 different performance levels, from the economical 1 watt per meter Kelvin SFR 100V to the high performance 3 watt per meter Kelvin SFR 300V. The standard thickness is 0.23 millimeters, but the higher performance 200 and 300V also come in a thicker 0.45 millimeter, creating an even stronger electrical isolation barrier without sacrificing thermal performance. The Surecool phase change thermal interface material is the ideal option when you have a very thin air gap and low clamping pressure between the 2 mating surfaces. The 5 mil thick material easily flows into microscopic gaps between the 2 mating components, where the material's high performance 3 watt per meter Kelvin thermal conductivity creates a superb thermal bond. Available in a single 3 watt per meter Kelvin grade, the 5 mil thick material handles like a die cut pad and naturally wants to stick to the mating surface. See our installation guide for more details. Surecool's double-sided thermal tape utilizes a fiberglass cloth carrier coated with a high-tech thermally conductive acrylic adhesive on both sides. The result is a thermal tape with unique characteristics. Unlike other thermal tapes that become less tacky at higher thermal conductivities, the Surecool Thermotape delivers extremely high tack and holding power, all while packed with a 1.2 watts per meter Kelvin thermal conductivity. This makes for a thermal tape that is up for the challenge of not only improving thermal performance, but also that exhibits substantial holding power. Currently available in a single grade, the Surecool Thermotape 120V is available in 2 ways. The first as a die-cut part with a release liner on both sides. The second as traditional rolls of tape with a release liner on the top side only, split down to custom widths. Sur-Seal's Thermal Design Guide, coming out by the end of Q4, will help design engineers select the right thermal interface material for their application. The design guide helps walk design engineers through the different material types, and then utilizing real-world data helps engineers quickly narrow down which exact product and thickness will be most ideal to test in their application. We believe that thermal data should be readily available, and so Sur-Seal has conducted extensive testing in order to provide design engineers with easy-to-use real-world data. Our test data not only provides the thermal conductivity of the material, but the thermal impedance of the material when applied under pressure or at a specified % deflection. Thermal impedance data is available in all Sharecool products and thicknesses to help guide engineers to the right material and thickness for their application. If you find that you need additional custom thermal testing completed, Sur-Seal's engineering team is at the ready to assist with our in-house EIM testing equipment. Additionally, Sur-Seal can conduct comparison testing where we provide one-to-one performance comparison data between Sharecool products and other products you may be currently using. This allows for a high degree of confidence when improving Sharecool products as a viable alternative to your existing thermal interface materials. While the aim is to narrow down the choices as much as possible, it is still Sur-Seal's recommendation that you test the 1 or more materials in your application prior to finalizing your design. We understand that this design and testing process needs to be completed as fast as possible. That's why Sur-Seal has developed a rapid sampling program designed to get sample material in the hands of engineers as quickly as possible. Just send us a request for a sample and we will ship out your sample the next day. Sur-Seal can provide a rapid prototype cut to the finished shape and size of your final design. Utilizing our toolless knife cutter, we can quickly cut and ship samples to you that are exact specifications. All we need is a 2D CAD file. Now I'm going to open the floor to any questions you may have. We have a team of application and material experts on the call who want to hear more about your specific questions on TIMs.
Hey, thanks, Greg, John, and the entire Sur-Seal team. That was a great presentation. I learned quite a bit. We have a few questions in the Q&A, and without wasting any time, I'm just going to hop right into it. So first question, What information do you need from me to help identify thermal solution options for my application?
Hey, Greg, do you want to take this one?
Oh, yeah, sorry. Yeah, that's a good question. We're looking as much information as possible from the application side. So the size of the components for the thermal material, the distance of the gap between the heat sink and the component generating the heat, as well as the typical operating temperature range for this application. And then anything related to pressures that are the amount of pressure being used, as well as if you need a PSA for the assembly process. So we like to work with our customers to get as much of that information up front to provide some good options for them to test.
All right, great. Next question. What method do you use for testing thermal properties of your product?
Yeah, so we use the standard ASTM D5470, which we use to modify per the application of the temperature for the customer, as well as the pressures that they see in their application. We get the thermal impedance is the main area of data we get versus pressure, as well as versus percent deflection, which we could use to calculate the thermal conductivity effectiveness.
Okay. And the final question, is thermal conductivity or thermal impedance more important when selecting a material?
Well, the thermal conductivity is the bulk through the material, but for an application purposes, thermal impedance will take into account the pressure, the thickness of the thermal material, and the size. So really, the property to go by for the application would be the thermal impedance.
Great. Well, that's all we have in the Q&A section for now. I want to encourage anybody who's attended this that if they have a question, please send them over and we can answer them after the fact. All Q&As answered in this session and throughout the entire Thermal Live event will be posted on the website after the event has concluded. Additionally, all these presentations will be available on demand in a video format after the event concludes. Once again, I want to thank everybody from the Sur-Seal team. It was a great presentation. I want to thank everybody for attending day one of Thermal Live 2021. I encourage you to attend the next 2 days. We have a full slate of technical presentations and product demonstrations. So once again, thank you. Day one was a major success. This technical session was a major success, and I thank everybody once again. Have a good day.